Hi everyone. In this video we're going to talk about acceleration. As we did with velocity, we're going to look at three cases. Bodies that are only translating, bodies that are only rotating, and then bodies that are both translating and rotating. Also, as we saw with velocity, acceleration, being able to generate these expressions, it's going to rely heavily on our ability to do product rule, to do chain rule, and also to apply the transport theorem. So if you are still struggling with those concepts, here's more practice for it. So let's go ahead and get started with the first case. For translation only, let's look at a block and a groove. At this point, we know how to set the problem up. We need an inertial reference point and an inertial frame. And we know for every body in the problem, we're going to put a point. Let's do the center of mass of the block. Let's call it point A. And we know that we need a frame attached to this block. All right. Next, let's do position vectors. So the position from N to A is going to be some translation in the x hat in direction. Here's that variable Q. And the rotation between the A frame and the N frame, there is no rotation. So xn equals xa and yn equals ya. All right. From this, we know that we can define the rotation formally. We know that xa is going to equal ya dot 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 for, oh, no, that's not it. xa is going to equal xn. There we go. And then the same thing for YA and ZA. All right, so that takes care of the rotation. Now, as for generalized coordinates, there's only the one generalized coordinate. There is no constraint on this problem. This block can freely move, so 1 degree of freedom. Let's go ahead and move on to velocity. The velocity of A is just ddt of the expression above, so that's going to be q dot x hat n, and we can go ahead and call out the angular velocity of the A frame. Since the A frame doesn't rotate, angular velocity is by definition 0. All right, so this is all review up until this point. So what happens next? Well, I usually recommend doing angular velocity before linear velocity. This problem is obviously very easy. Similarly, I would recommend doing angular acceleration before angular velocity, or sorry, before linear acceleration. So, angular acceleration, this is how we define it. It's omega into A, right? That was the angular velocity with a dot. So, omega into A dot. This is your angular acceleration. The definition of this is ddt of omega into A. Of course. Since this one, since the velocity is 0, the acceleration is also 0. All right, so that's out of the way. Let's do linear acceleration. So VA is velocity, VA dot is acceleration. The definition of this is ddt of VA. So ddt of q dot x hat n. We could, if we wanted to, do a product rule expansion on this. We know, of course, that the n frame doesn't change. So this is q double dot x hat n. All right. Nice and easy. So that's it for this block. Let me clean this up and we'll move on to a rotating body. For rotating body, we're going to do a pendulum. I've gone ahead and I've put in an inertial point, inertial frame, and then a body attached point and body attached frame. So let's do, we know what to do with the rotation, of course. We've done this numerous times. We're looking at a simple rotation around a shared z-axis. So do your diagram. Here's going to be our generalized coordinate for this problem is theta, xn, xa, yn, and ya. And of course, from this, we can generate the trig expressions that will define the rotation itself. xa is equal to cosine theta, xn plus sine theta yn plus dot, dot, dot. Okay. And we also know what we're going to do with the position vector for this one. Let's call this length L. So the position vector from N to A is L x hat A. All right. So position and rotations are taken care of. One generalized coordinate, right? It's only the angle theta. No constraints, 1 degree of freedom. So let's define the velocity level next. Angular velocity first. We're doing this just from inspection. This thing is doing a simple rotation around a shared z. The angle was theta, so we're looking at theta dot around z hat A. Next, the linear velocity of point A. We know that this is ddt of PNA, and from the numerous times that we've done this, we know that the answer is going to be L theta dot y hat A. All right. So there's position and velocities are now done. Let's do the acceleration. Again, I recommend doing angular accelerations first. So omega into A dot, and this is ddt of theta dot z hat A. We could do a product rule expansion on this. Z hat A does not change, right? The A-frame is rotating, but it's rotating about a shared z-axis. So z hat A does not change. And then we just have derivative of the scalar theta dot. So theta double dot z hat A. All right. Just to give us a bit more room, because linear acceleration does get a little more complicated, let's erase this. Now, let's just write down VA again. VA is L theta dot YA. All right. We want the linear acceleration of point A, so that is VA dot, and the definition of this is ddt of VA. So let's take this and just bring it down. VA is going to be ddt of L theta dot YA. All right. Before diving into this, let's just take a look and see what we expect to happen. We're going to take this derivative and we can do a product rule expansion. There's 3 terms in this expression. There's the L, the theta dot, and the Y hat A. We know that if we needed to, we could go back to the definition of the rotation. We could replace the Y hat A with, it's going to be negative sine theta, x hat n plus cosine theta y hat n. We know that we can do that and go through it the long way, but we're not going to do that. We're going to use transport theorem. Now, when you're first getting started, to help you, right, to help you get started on this, I recommend looking at these expressions and counting how many of them are variables, how many of these terms change. Well, the L is a constant, but the theta dot is a variable, and also y hat A, right? Inside of the y hat A is the angle theta, so theta dot changes and theta changes. So when we do a product rule expansion on this, we should expect to have 2 terms at the end of this process. So let's take it slow and let's show all of those steps. VA is going to equal, and I'm going to do the full product rule expansion. This is ddt of L times theta dot YA plus ddt of, well, let's write it this way. Let's say L ddt of theta dot y hat A plus L theta dot ddt of y hat A. Now, we had 3 terms here. I went ahead and did a full product rule expansion. This first term is of course going to be 0 because d dt of L being a constant, this one is 0. So I'm going to erase the top and I'm going to leave this and we're going to start writing again up here. What's going to happen in these next terms? Well, in the middle term, we're taking d dt of the scalar theta dot. So this generalized speed is going to become a generalized acceleration. And then in the third term, we've seen this before, we're taking d dt of a moving frame. And we know that we can replace this expression then with transport theorem. So let's rewrite it. VA is going to equal, this first term is gone, this second term is just d dt of the scalar, so L theta double dot y hat A. And then the last term, we're going to do transport theorem, so plus. Now, remember when we do transport theorem, what frame are we taking the derivative of? We're taking the derivative of a frame. Frame A. So this is plus omega n to A. If that was frame J, it would be omega n to J. We're going to do a cross product, and then we have to put something, right? We have to put something inside of this cross product. Now, what goes inside of this cross product was the original quantity that you were taking the derivative of that yielded this product rule expansion. So what goes inside is L theta dot y hat A. Notice that we don't put inside of this Lx hat A as we did when we were deriving the velocity, right? When we're deriving the acceleration, we're taking the derivative of this, and that is what yielded this product rule. So we need to do omega cross this velocity. All right, so what I'm going to do is I'm going to put in the definition of omega into A because we defined that before. So omega into A is theta dot z hat A. Now, there are of course several ways you can resolve this cross product. First, let's bring down this term L theta double dot YA. And then what is going to happen with this cross product? Well, Z cross Y is negative X. Go back and recall all of your cross products. Remember that X cross Y is Z, Y cross Z is X, and Z cross X is Y. Now, the one we're looking at is this one in the middle. The order has been reversed. It's not Y cross Z, it's Z cross Y, so it becomes a negative. So what I usually do is I usually just take the scalar components and we multiply those. So this is L multiplied by theta dot squared. And then Z cross Y yields negative X hat A. So the final answer, VA, this is L theta double dot Y hat A minus L theta dot squared X hat A. All right. If you'll recall from previous discussions when we were doing velocity, we said that the different terms in the velocity expressions had names. And I didn't mention this on the previous problem with the block, but I'll just kind of put it over here in the corner. A moment ago when we were looking at the sliding block, the expression came out as VA dot was Q double dot X hat N. All right, and then this time, when we had a rotating body, we now have two terms. So on the velocity level, we had two different types of velocity. We had slip and we had tangential. Well, this is still slip. This is now a slip acceleration. And then this term, this is still a tangential. Now we have a new term. that we haven't seen before. This one is called normal. And on the diagram, I think it's always useful to take these and relate them to the image so you can see what's happening. So we can do this block first. What's going on with this slip? Well, it just has an acceleration in the direction of the groove. If there is a force being applied to this block and you have some net force on it, right? If the friction doesn't cancel it out, then this block is going to experience a net acceleration in the direction of the applied force. So this is a slip acceleration. This tangential acceleration, the direction is y hat A, which puts it in that direction. And notice that this term is dependent upon there being a theta double dot. Consider you could have an object, this pendulum, that is that is rotating at a constant angular velocity. If it's rotating at a constant angular velocity, then it has no angular acceleration. So theta double dot would be 0. However, if it is rotating, even if it's rotating with a constant angular velocity, it will have a normal acceleration. And the normal acceleration points in the negative x hat n. Negative x hat A. Now, some more comments. Theta double dot could be in the other direction. You could have some negative torque being applied, some negative moment being applied to this this body. For example, if there was no motor or any active torque at this joint, and we simply had this pendulum as is and we let it go, the force of gravity is going to cause this thing to fall in this direction. It's going to have a negative moment, and that would lead to a negative angular acceleration, and then this linear acceleration, right, would become a function of a negative theta double dot. L is always positive and y hat A is just the direction. So in that case, the linear acceleration of point A, the tangential component of it, would be in this direction, right, if the theta double dot was negative. So the tangential acceleration can change direction depending on the angular acceleration. Now, notice that in the normal component though, L is always positive and x hat A is just a direction. What if this pendulum is rotating with a negative angular acceleration? It actually doesn't matter because it's squared. So you lose the sign on the theta double dot, and the normal component of the linear acceleration always points towards the location of rotation. Now, perhaps you've heard that before. Planets rotating around the sun are actually always accelerating towards the sun. The moon rotating around Earth is always falling, it's always accelerating towards the Earth. And this is the normal component of that acceleration. And really what this is responsible for is just creating the trajectory, the curve trajectory around the center of rotation. All right, so what's going to happen in the next problem when we put these things together? What happens when we have a body that is both translating and rotating? So we'll see, right? Let's find out. So let's clean this up and let's do that last case, the rotation and translation. For the third case, rotation and translation, let's take that same pendulum and let's cut a groove in the pendulum, and into the groove we're going to insert a block. So the pendulum is going to rotate and the block is going to rotate with the pendulum. So you can see that I've put the A frame and the B frame together. Those frames are aligned. Inside of the groove, the block is free to translate. So we need a translation variable to track that motion. So let's use the translation variable Q. All right, you know how to set up the coordinate frames. We can do angular velocity into B, and this is going to equal angular velocity into A. So that is our theta dot. Now, we could call this Z hat A, we could call it ZB, we could call it ZN. We know they're the same thing. And let's do let's do positions. So P into B, this is Q in the x hat A, and then the velocity of point B, again, we've done this. We know that this is Q dot x hat A plus Q theta dot YA. So on the velocity level, we can see that the block then experiences both a slip and a tangential velocity. All right, so let's talk about angular acceleration. So omega into B dot, this is ddt of theta dot ZB. So this is going to be theta double dot ZB. All right. Next, let's set up the linear acceleration of point B. So this is VB dot, this is of course ddt of VB. So what I'm going to do is I'm going to write it here with the ddt already distributed to these two terms. ddt of Q XA plus Q dot XA plus Q theta dot YA. Oh, broke my own rule. Okay, plus ddt. All right. We've distributed the ddt. Good. So what are we going to do? Well, now we have both of these terms that we have to resolve. So let's take this expression. I'm going to write it up here. And before we do, let's consider what's going to happen. We know that we're going to do a product rule expansion. In this first term, both the Q and the x hat A are changing. And then in the second term, the Q and the theta dot and the y hat A. These are all going to change. So out of this first term, we're going to get 2. Out of the second term, we're going to get 3 from those product rule expansions. VB dot equals. So the product rule expansion for the first term. This is, we'll take it slow and do the full thing. So ddt of Q dot x hat A plus Q dot ddt of XA. Next, plus. So now moving on to the third term, or sorry, the second term. This one's going to yield 3. So the first is ddt of Q dot, and then that is multiplied by theta dot y hat A. Oops, I apologize that, there we go. It's just ddt of Q. The next term in this expansion is going to be Q ddt of theta dot y hat A, and then the final term is going to be Q theta dot ddt of y hat A. All right. So what's going to happen to these terms? Well, this is derivative of a scalar. This is derivative of a scalar. This is derivative of a scalar. The other two are derivatives of the coordinate frames, the moving frames. So we know that these two terms we can replace with transport theorem. VB dot. ddt of Q dot is going to yield Q double dot x hat A. We've seen this before with the translating block, and this is a slip acceleration. Next. Plus transport theorem for this one. We're taking the derivative of XA, so omega NA cross. The term that yielded this product rule expansion was Q dot x hat A. Next, ddt of the next term. So ddt of q yields q dot, and then multiply by theta dot y hat a. The next term, it's ddt of the theta dot. So plus q, ddt of theta dot yields theta double dot, still in the y hat a direction. And now the last term, we're going to replace this one with transport theorem as well. One thing to take note of, it actually doesn't matter. It's not going to specifically matter whether this is x hat a or y hat a. As far as this first part goes, you still take omega in a cross. Now, what goes inside of these parentheses? It's whatever term yielded this product rule expansion, and that was q theta dot y hat a. All right, so some of these terms are finished. For example, that one is done, this one is done, and this one is done. We have these two terms to contend with. Omega in a is theta dot ZA. And of course we could write this as omega in a ZB, and of course XA is equal to XB. All right. And then this one is theta dot ZA as well. All right. So let's erase up here and let's finish this one off. So VB dot equals, I'm going to bring the ones that are finished. So Q double dot X hat A. What's going to happen to this next term? Well, this is theta dot times Q dot. So I'm just going to multiply the scalars. So plus, and let's put in this order Q dot theta dot. Now, go back to your cross products. Z cross X yields positive Y. So YA. This transport theorem became this expression. Next, we can take the next term and we can bring it up. Notice that this one is also Q dot theta dot Y hat A. Take that term at the end, bring it up Q theta double dot Y hat A. We've seen this term before. This is our tangential. And then this final term, we have actually seen this one as well. Take the scalars and multiply those. So it's going to be plus Q theta dot squared, and Z cross Y is going to yield negative X. Okay, so let's erase this one on bottom. And let's clean that expression up a little bit. VB dot equals, I'm going to bring Q double dot down, X hat A. I'm going to combine these two together. So 2 Q dot theta dot YA. I'm going to bring down the Q theta double dot YA. And then we're going to bring this one down. I'm going to move the negative in front. So minus Q theta dot squared X A. And there we are. So that is the linear acceleration of a point on a body that is both translating and rotating. So this is slip, this is tangential, here's our normal, and here's a new term now. This term is called Coriolis. Okay, some interesting points. Notice how slip and tangential, these are both functions of accelerations, right? So we have a linear acceleration. This one was required, or this one was dependent on some force acting on this block in the direction of the groove. Similarly, we've seen the tangential before. This is dependent upon an angular acceleration. Both of these can change directions depending on the q double dot or the theta double dot. In this particular case, the q has to be positive. However, we could have a problem where suppose you're rotating about a point in the middle and the pendulum is like this. So you could have a situation where the block can translate to both sides, and the block, the value of q then could be negative. So in this case, that q being negative would cause the tangential to change sides. We've talked about normal, how normal has to always point towards the center. And now this new one, Coriolis. Coriolis is interesting. It's a nonlinear combination of a linear velocity and an angular velocity. So consider for a Coriolis acceleration to be present, two things have to be happening. Number one, the pendulum or the body has to be rotating, and the block has to also be translating. If either of these is zero, so if you have an instantaneous linear velocity, a slip velocity that is zero, you do not have Coriolis. All right, so this is the most general case. And what you can do in your problems is you can actually go through a problem and you can just look at a body and you can say, is that body, is there a rotation variable? Is there a translation variable? And before you get started, once you get accustomed to this process, you can actually call or predict how many of these different acceleration terms should be in the final answer. Okay, what I want to do is I want to do one more example in this video before we call it, and that example is going to dive into this. Omega in A dot equals ddt of omega in A. Now, when we talked about angular velocity, I said that we can usually define this just from observation. We can look at the problem and we can make a call on this. I do not say the same thing about angular acceleration. In the problems that we've done, it's been theta dot and theta double dot, and it has seemed very easy to do angular acceleration, but there are cases where this actually gets much more complicated. So we're going to do another quick example where we show how this can become more complicated. But as far as the linear acceleration, this is as complicated as it gets. Now, you could have a mechanism with a series of bodies kinematically linked. You could be doing loop constraints, for example, and you could have, this component plus a whole lot more depending on how long or complex the original position vector was. But for a single individual position vector, a distance in a particular frame, you can have at most 4 of these terms. All right. So we're gonna do this last part where we talk about this. We are going to have another few videos of just doing some worked examples with linear acceleration, and specifically with acceleration constraints. So we've done position constraints, we've done velocity constraints. There are also acceleration constraints. Now that process isn't any more difficult than you would expect. If you take ddt of constraints to get velocity constraints, you take ddt of those to get the acceleration constraints. But I will do a video where we practice it. Okay, let me clean this up and we'll talk about this fun case. For this final case on angular acceleration, we're going to dip back into our 3D problem. Recall that we did this one in a previous video and we calculated the linear velocity of a point down here at the tip of this second pendulum. So the first pendulum is rotating about a shared z-axis. Here's our 3-dimensional inertial frame. And the first pendulum is rotating about the shared z. And then the length of this pendulum is defined in the xa direction. And then there is a rotation about this point. There's a joint here. And now there's a rotation about this shared x. So this is both the xa and the xb. And then the length of this pendulum we called the YB. There we go. Sorry about that. We called the YB, and then the ZB was coming off perpendicular to both of those. Now, what I want to do, we're not going to go through the whole process of finding the linear acceleration of that point. We could. It would be a little tedious, but we absolutely could. But what I want to do is I want to use this example to talk about angular acceleration and why it's not always as obvious as you think. So we have omega in A and we have omega A to B. Notice that in this case, because this is a 3D problem, and we first did a rotation about a shared Z and then we did a rotation about a shared X, in this case we have to use relative angles. So there's first an angle from the N frame to the A frame, and then theta 2 goes only from the A frame to the B frame. The total angular velocity for the B frame, omega n to B, is the linear addition of both of these. So theta 1 dot ZA plus theta 2 dot XA. Now, if I asked you for the angular accelerations, angular acceleration of the first one, that's easy. Omega in A dot is going to equal theta 1 double dot ZA. Now, when you go to do omega into B dot, you may be inclined to say, well, this is theta 1 double dot ZA plus theta 2 double dot XA. That is, however, incorrect. Let's talk about why. So here's our description. We know that omega into B, if we go back to the definition, is ddt of this term. So theta 1 ZA, and I'm going to go ahead and distribute the ddt theta 2 dot XA. All right. So omega into B dot, what is going to happen? Well, this term is obvious. This is theta 1 double dot ZA. However, what happens on this term? You can do a product rule expansion on this, and notice that the X hat A term changes. So, this is ddt of the theta 2 dot is going to yield theta 2 double dot X hat A, and then we have to say plus, and I'm going to write the transport theorem for this one. Since we're going to be taking ddt of X hat A, that means we need omega into A. So it's omega into A cross, and then what goes inside of the cross product? Well, what did we take the derivative of, right, that would yield this? Well, it's theta 2 dot X hat A. Okay, what is omega into A? We have it right up here. It's theta 1 dot ZA. All right, let's make ourselves a little bit of room. Omega into B dot is going to equal, these two are both finished, we can bring them up. Theta 1 double dot ZA, theta 2 double dot XA. And what is going to happen with this cross product? Well, we can multiply the scalars together. So I'm going to say plus theta 1 dot multiplied by theta 2 dot, and then Z cross X yields positive Y. And there we go. That is the angular acceleration of the B frame of body B, which got a little erased. That's okay. So when you were doing three-dimensional problems, if you have kinematic chains that are rotating about multiple axes, and of course we had to use these relative angles, you could end up with expressions that look like this. You could have theta double dots, and you could have this combination, this product of theta dot terms. Now, let's just consider the units in all of this. The units of a theta double dot, well, that's radian per second squared, And then here we're looking at a combination of radian per second and radian per second. So in both of these cases, of course, radians are related to the arc, right? You can go all the way back to your trig classes and you can look at unit circles. And we know, for example, that if you were to take something like, let's say we were talking about those linear accelerations we were looking at earlier. If this was really some term that was q times theta double dot, then we know that the units of q would be meters. So we're looking at meters multiplied by radians per second squared. So this is going to come out as meter per second squared along a curved path, right? We know that that's the roll of the radian. That's effectively what's going to happen here. It is radian squared per second squared, but again, if you take this and you multiply by a translation variable, you're still going to end up with meter per second squared. Okay, so that's it for this video. If you can do velocity, I expect that you can do acceleration as well. It's just more the same procedure, right? It's more derivatives, it's more product rules, it's more chain rules. All right. So we're gonna, as I said a bit ago, we're gonna do some other videos where we look at more examples of these, but this is it for today. So stay safe, everyone. I'll see you around. Good luck.